Well, as far as I know, I'm recording. So let's begin. So today we're going to talk about ANOVA. First of all, what can ANOVA do? ANOVA, even though it's called Analysis of Variance, that's what the acronym stands for. We're going to analyze the difference between multiple means. And that should be done when we have more than two groups, ideally. It can be used with two groups, but a t-test would make more sense in that situation. So if we have more than two means to test, the ANOVA is one of the best ways to do that, or at least in this case. So that's what we will do. And as multiple levels and factors get increased, ANOVA can handle that and is robust in analyzing that for reasons that we will mention later. So how does it work? Just a really brief description of how it works. It's essentially looking at the amount of variance between groups and within groups. So it's looking at the variance between those, and some names that we're looking at: the mean sum of squares, and we're looking at sum of squares between, sum of squares total, and when we figure those things out, we can find an f-stat, and then we're looking at that f-stat and the probability of achieving that f-stat and if it's significant or not. And when we look at that, we figure out, well, let's say it's significant, then we find that because it's an omnibus test, we don't know where that significance lies, so we do a post-hoc test. So we'll talk about that a little bit later and then run that through R. So assumption-wise, we have three main assumptions. Normality is the first one. Independence of cases is the second one, and the third one is homogeneity of variance. And we will actually test that in R in a couple minutes here, or a couple seconds, depending on how long that takes. So let's talk about my research method. Well, my research idea. So I thought about applying it to industrial psychology. And so let us say that we have a group of, let's say, 60 people, sort of an arbitrary number. And we're gonna use a weighted application blank, and we're gonna derive a total score from that using traditional methods. And then from there, we're gonna band them, if you will, into three groups. The three groups we can call high, medium, low, another arbitrary name. And so those are going to be the three levels to our factor. And from there, we're going to have them take a clerical test, because these are going to be clerical workers. And that's going to produce a score, which will be our dependent variable. Okay. So let's look at my data set. First, to find that, we're going to use the read Excel function through library. So we're just going to open that up, and that opens up the read Excel document, and that's essentially just a package that easily extracts data from Excel. There are other methods to extract data, which I traditionally use, but for some reason this time I chose this way. So let's go to line 2, ANOVA example data file, read Excel. So that right here is the location of my data file within my computer. So we're going to bring that up, and that, as you can see, that brought that over to my environment here, ANOVA example data file. And you will see what that looks like in a second. I kind of saved myself a step and organized it how R enjoys reading it before that. So we're just going to look at it here. Yeah, damn, that's pretty. You know, that's pretty because I created it, but instead of reorganizing it, I ended up making two columns. This is the group, and these are their scores there. As you can see, the three levels that I talked about: high, medium, low. So I just coerced them into that to make myself have one less step. Okay, so we're going to go to line 4 here, library. That's opening a package up from my library that I previously installed. And this is essentially just a data visualization package in R. We're just going to open that up and create a box plot just to kind of visualize our data. And that pops up here. And yeah, so it just pops up there. So we're going to move on now to this. So essentially, we're going to treat the variables as factors. And to run ANOVA, we're going to need to do that. So we're just going to push that into group here. Voila. On to the next one. As I talked about before, we have certain assumptions that we probably should not violate, even though ANOVA is a robust test, but we're going to check that just to make sure. This one is called Levine's test, so here we are going to run that. This is the function that we are running there. So we have some output here, and the main thing we're concerned with, we have an f value here. What is the significance of achieving that f value? And as you can see, it's not significant, so counterintuitively we can assume that we do have homogeneity of variance, which is an assumption that we probably should not violate. But there are corrections for it. So next line, line 9 here, attach. I'm not going to try to explain why I did attach because I don't have an impetus for it. But I think when I was originally running it, for some reason, because of the idiosyncrasies of R, I don't think it was running without it. But essentially, we're just pointing R towards this data file once again, even though it already was looking at it. But regardless. So now we are going to run the ANOVA here, ANOVA out. So that's essentially what I'm calling calling the output there, telling R to call it that. So we have the ANOVA function here. And then we have the x and y variable with the tilde in between. So that's what it's looking at here. And we produced our ANOVA, but it doesn't look too easy to read. So what we're going to do is we're going to create a summary output, and that's going to pop that down here. So I talked about earlier about mean sum of squares, degrees of freedom here. Now we're going to look at this f value, 2.4, not too large, but what is the significance of that? It is non-significant, and because it's an omnibus test, I guess in this case what we're going to accept the null hypothesis that there is no difference between groups. But hypothetically, if we did achieve significance here, according to the traditional 0.05 arbitrary number, then we would have to do a post-hoc test because it's omnibus, so we don't know where the difference lies. So the way we are trying to do that is to run a Tukey. So we're going to run a Tukey. We ran it here, and as you can see, it breaks down a pairwise comparisons between all groups, all possible combinations between the groups, and these would be the significance levels there. And obviously we have not achieved any significance between groups at all because in our omnibus test we did not have overall significance. But if we were, this would provide us with that insight of where that difference lies. And just as a brief pointer, we do the Tukey instead of doing multiple t-tests because we want to mitigate the possibility of family-wise error. Okay, so final step, we're going to do library sjstats. This is just a stats package that happens to contain the omega squared function that I wanted to use. It seemed to be the most efficient way of achieving effect size. So this function is contained in this package. So we're going to run that. And we have a fairly small effect size as expected. So let's just look at if I covered all my bases here. So yeah, just a brief rationale if I didn't already mention it. We do have a situation where a one-way ANOVA would be appropriate because we have a one factor with 3 levels. So we're trying to test multiple means. So that was the reasoning for choosing the ANOVA test, aside from the reason that I was told to choose it for this assignment. Okay, so we did that. So what can we conclude from this? We can conclude that, in a roundabout way, we can kind of conclude our weighted application blank is not really predicting high performers well because there's no difference between groups. So kind of an alternative hypothesis would be in a perfect world, we'd expect our high group, our high performers, on our initial predictor test, we would expect higher scores on here. So we would expect a significance difference between groups, especially between high and low. We would still want to differentiate between high and medium, and that is ideal. So intuitively, I would say we need to go back and look at our weighted application blank, because we are not really achieving predictive validity, although that would be a different coefficient measure. But it can kind of be assumed that we do have an issue with that. Yeah, I think that's it. I will come back and mention anything if I realize that I missed something. But yes, all right.